appreciate you showing up on the short week. So I'd like to start us off by talking about free money. Woo! Everybody loves free money. Well, this money is definitely not free, but who here is an American citizen? Oh, awesome. Actually, a lot of you. Not that I don't like the rest of you. But I want to let you know about, because I realize I don't think I've done this yet, is that we have a scholarship for service program here at ASU funded through the National Science Foundation. So the National Science Foundation just gave us a $4 million grant to give out scholarships to students. It's actually a super cool program. To be eligible, you have to be a U.S. citizen, and the idea is for every year of, so they'll completely pay for your tuition, as well as, let's see, full-time tuition and education reimbursements, book allowance plus a stipend, so you actually get paid to go to school on top of tuition and everything. And in exchange, you agree to go work for the government for every, it's like roughly for, let's say they pay for a year of your schooling, you go work in the federal government for a year. And this is specifically around security. So the idea is that they're going to pay for your education and you pay them back by working for them. Otherwise, you have to pay back all the money, and it's a whole thing. Question?
Yes. Is it retroactive?
Is it retroactive? No. No. But it is very soon to be active. So if you actually get your application in like the next week or two, they can actually start funding you starting spring 2018. So if you have one more semester left, then even yes, you could do that.
I have 2 weeks.
2 weeks is probably not enough. So U.S. citizen, this is bachelor's and master's, so even if you're doing your master's, you can do this. The idea is, so you do internships during the summer, we fly you out to DC so you can go to job fairs and talk to interesting people there. So some of the people who've gone through there that I know have gotten jobs at like the NSA and various other organizations. So this is a super cool program. I think it's nice to get paid to go to school. Plus, after usually you'll get security clearance as part of this. Most of the jobs require you to get security clearance. And so you go do your time working in the federal government, and then you're actually completely set if you want to continue on public service path, or you want to go into industry and make a ton of money because you have clearance and you have the experience of actually working in a real organization doing security stuff. And it's super easy to apply, that's the other thing. It's just an application form with your resume and an official transcript. It's really easy. This is an old out of date, but if you would like to talk to, you can email me. I'll send you to Dr. Yao. Dr. Yao is in charge of organizing and managing the program. Any questions? It's super cool, I promise. All right. Where am I going? Okay. Cool. Okay, so we are, before we get started on this, assignment 4 is going to be up today. It's going to be super fun. It's going to be a binary server where there will be options of different challenges, and you will have to break these services challenges in order to get points. You get points for how many that you break. I don't know the exact breakdown yet, but it will be super fun, I promise.
I highly doubt that.
You highly doubt that? Well, it'll be fun. Fun for me, anyways. So I guess before I send out an email, because this will be like a shared server, I've tried to put protections in place, but don't be overtly malicious in the sense of like trying to DOS the server. That's super lame. What else could you do? Don't write a thing that uses up all of the free space on the server, because then I just have to go in and implement things to stop that in the future, and it's really annoying for me. So don't do that. were talking about command injection, and the example I want to bring up is a bug called Shellcode. Does anybody remember this? Hearing about this? A few people. So this was a bug in September 2014 that had existed for about 20 years in Bash. So the idea was we've seen that environment variables are basically inherited from one program to another, and Bash actually passes its environment variables to other instances of Bash. And in addition to passing variables, which you think, yes, of course, that makes sense, you can actually pass in functions to other instances of Bash by setting an environment variable whose value starts with parentheses, like open and close parentheses, and then the function body that you want. So the first thing Bash does when it starts up is look at the environment variables and see is there any variable names that start with these parentheses. If so, then it basically evals that code. And so by appending commands there, you can basically execute arbitrary functions. So this was a huge problem when we talked about GitHub actually allows you SSH access to their servers in a very limited way. Well, they're actually running Bash, and so you can actually pass this environment variable of SSH original command to, let's say, access the etc shadow, CGI web applications. So this is basically, so CGI web applications are web applications that are executed as if they were a binary, and they get their inputs from the environment variables. And the environment variables are controlled by the user. So the user can make requests to a web application to get arbitrary code execution without any like authorization. All you need to do is make a web request. That's why this is actually a really big deal. I think this may have started the cool vulnerabilities with cool names and logos. If you want to look at the Shellcode logo. Cool. All right. So,
Is that really a bug or was it actually a feature? Because I mean, it sounds like that would be something kind of useful to maneuver and do things within your own system.
I think it's one of these cases where, as it was originally written, was probably a feature that then, when Bash started to be used in all these different cases, became to be a huge security bug. And I think the documentation around this functionality was incredibly poor as well, in the sense that normal people, like almost nobody knew about this functionality, and so it was basically just code that nobody ever used, but it included this functionality. So yes, it's kind of the thing of like a feature. If you change the environment, right, or take an application, put it in a different environment, that feature could now be a security bug. Cool. So now we're going to talk about buffer overflows. So this is going to be our introduction to kind of one of the core security vulnerabilities in applications. And that is something that is so silly that it seems like, why should this ever even be a problem? And that is the lack of boundary checking when you're writing C or C++ applications. So what do I mean by boundary checking here? What boundaries do I care about checking?
The buffer that you're putting, so
What is a buffer?
you'll have some sort of space allocated for a string or something, expecting input, say someone's first name, and if they are just going to put in their first name, it's no problem, I'll make it like 200 characters or something like that. But if they know that there's a possibility that I did something like that, they can put in a massive amount of characters which would overflow that buffer, and then you can get into other areas that are on the stack.
Exactly. So I think I explicitly had a test case on assignment 1 on the Secure This House, where I just made absolutely huge like people names, because the spec didn't say anything about what size they were. So if you're writing a C program and only had, let's say, allocated a space of like size 100 to read people names, that should crash that program. These are still one of the most popular types of attacks. They can be, and they show up in all kinds of different applications. The actual exploit is going to be architecture operating system dependent. You can run these both locally or remotely. And the key capability that a buffer overflow can allow is it can allow you to alter the code or the data of the application. Well, sorry, I guess I should rephrase that. The data, you can alter the data of the application, and you can alter the control flow of the application. So what's the control flow?
What the program's going to do next.
Yeah, what the program is going to do and execute next. And it's actually a way we're not used to thinking about programs, right? We look at the code and we can see, okay, this main function starts to execute, so line 1 executes, and then 2, and then 3, and then depending on this branch condition, line 4 will execute, or line 5 will execute, and after that, this function will get called, right? It's very easy and clear to see the control flow. There's actually a lot of research into how to automatically exploit these vulnerabilities, so there actually are tools out there that can find buffer overflows and automatically generate an exploit for them, which are very cool. And there's also a lot on the flip side of saying, okay, how can we actually prevent the successful exploitation of these attacks? So there's mitigation techniques, and of course you have this awesome, this is one of the reasons I love security, is because you have this awesome arms race where the attackers say, okay, we're gonna exploit buffer overflows to hijack the control flow. And the attackers go, great, we're going to completely randomize the memory layout so you never know where the stack is. And so they go, okay. And so attackers then say, okay, then we'll up our game and we will figure out, as we'll see, we'll do return-oriented programming or return to libc techniques so that I don't even care where the stack is. And so then they say, okay, well, let's change the location of libc. And then it's this escalating game, but attacks always get better. So without fundamentally solving this issue, you're still going to have these types of attacks. So in order to understand that, we need to understand the stack. This should be familiar to you if you took 340 with me. So what is a stack in terms of the computer architecture? So not the abstract data structure of a stack. What is the stack?
Essentially scratch memory for functions.
What does that mean?
So anything that your program needs for memory, such as local variables, it'll put on the stack to use in that scope, and then
can I put it anywhere onto the stack?
What?
Can I put it anywhere onto the stack?
Currently where the stack pointer is pointing to.
Right, so similarly to the abstract stack data structure, right? We push things onto the stack and then we pop things off the stack, but it's not just a huge array that we can write wherever we want to. But yes, great. And as we talked about, we'll start at high memory addresses and grow down, so the stack will be growing when it is decreasing in value. That's actually a tricky thing to conceptualize, but it's fine. And a function, so a function can do whatever it wants in the stack. So it can use this essentially as scratch memory, as we said. And the assembly language really does support this mechanism on x86. So the register ESP holds the memory address of the current location of the top of the stack, or if you think about stacks as you put things on, that'd be the top. You could also say it's the bottom when you look at it our way of high to low. And so we have instructions like push EAX, which says store whatever's in the register EAX on the stack and move the stack down enough to make room. We have pop EAX, which does the reverse, which moves things off the stack. So here's a brief example. So we have all Fs, all zeros. We're at memory location here, hex 10,000. So if this is our stack pointer, so if I tell you this is the stack, this is the top of the stack is hex 10,000. What's the value that's going to be in ESP? Hex 10,000, exactly. So these two are intricately linked. You don't know where the top of the stack is if it's not in ESP, right? Whatever's in ESP is that. So what do we know about everything in our diagram above address 10,000?
It's got important stuff in it.
It's got important stuff in it, right? That is all in the stack. And everything, by that same logic, then everything below that should be not important stuff or garbage, right? Stuff that we don't care about. So if we have some super simple instructions, push EAX, push EBP, if our registers look like this, where we had 10 in EAX and 0 in EBX, ESP, as we said, will have hex value 10,000. We'll start here, we'll push EAX, which actually means that the stack pointer will be decremented, so the stack pointer will move down 4 bytes, and EAX will be pushed. The value that's inside the EAX register will be put into memory at where the stack pointer is pointing. And no, we're not drawing this 100% precise because this would be 4 bytes, so it would be 0000A. I don't know which order, that would be the Indianness, but we'll ignore that for now. And finally, when we pop EBP, we will take that, we will first take the value that's at currently where the stack pointer is, take that hex A, copy it into EBX, and then increment the stack by 4, essentially freeing that memory and saying, okay, that's now, we can reuse that memory, right? So we just did 2 instructions that essentially copied EAX into EBX, but using the stack. Questions on the stack? Cool, this should be a refresher. All right. Now we need to understand really the problems of a buffer overflow. We need to understand, so what is actually stored on the stack? So, as already mentioned, the stack is used for scratch storage. One of the main reasons is for local variables. This is where local variables are stored for each instance of an executing function in the current call graph. So the idea is that basically the currently executing function will have its frame pointer in EBP. For ease of use reasons, we don't want to use the stack pointer to reference into our function frame, so it looks something like this. So we have our main function, we have local variables A, B, and C. A is 10, 100, 10.45, A is equal to A plus B, return 0. So what the compiler does when it sees local variables, it basically generates an offset from EBP and says, okay, at EBP, A will be at some EBP plus A value. And everywhere in this function, to every reference to this A, I will use EBP plus 4. Same thing with B and C. And then compiling the code actually becomes really easy because you say, okay, at the memory of EBP plus A, set that equal to 10. At the memory of EBP plus B, set that equal to 100. And so forth, 10.45, and then finally A is equal to A plus B. So it's kind of a pseudocode translation of what's going on there. And then it compiles it actually out to x86 code. So for instance, the compiler can choose whatever order it wants for A, B, and C. It does not matter. There's no specification that says it has to do it one way or the other. Historically, it's usually, well, I think it's usually in this order where it's kind of where, let's see, A will be at the most bottom, so we have A, B, actually I take that back. I have no idea what order it's going to be in, but the truth is, to figure out the order, you have to look at the assembly code. If you're ignoring the assembly code and just looking at the C code, there's no guarantee that they're even related at all. All right. So we have EBP minus C, B, EBP minus 8, C is at EBP minus 4. We're going to move, so the first thing that needs to happen when a function is first executed, it needs to create space for its local function frame. And it needs to store the previous stack pointer because the current base pointer will be the function of whoever called it. So the very first thing it does is, well, let's go through this. All right, let's ignore that for now. It needs to create space on the stack, so it creates 16 bytes on the stack by decrementing the stack pointer by 16. So this is another one of these things where subtraction is actually getting you more space on the stack. We then move A into EBP minus C. We move 64, which hex 64, which is 100, into EBP minus 8. We'll move this crazy value into EAX, and then move EAX into EBP minus 4. What's this crazy value? 10.45 in floating point. And then we will move, let's see, EBP minus 8. So what's EBP minus 8 here? B. And what's in B right now? 100. So it's going to move 100 into EAX. It's going to add EAX to EBP. Is that right? Yeah. Into EB with EBP minus C. EBP minus C is A. Wait, that's not right. Okay, move this into here. Yeah, okay, move B into A, add B. Oh, A is equal to A plus B. Yeah, okay, easy. Okay, so when you have a 2, so add, you usually think of it in this way, of A is equal to A plus B. Here you have add EAX to EBP minus C, which is A, so what was in B, you're adding to A, and then the destination is the second argument here, so saving that value back in EBP minus C. Okay, cool. So looking at how this all actually works, so we will have our stack pointer here. So we first have to subtract 10 from ESP, which is, well, decimal 16 base. Yeah, so 16 here. So now this is our function frame. So now we have 2 pointers. So there's 2 arrows here, right? The arrow at 10,000 is our base pointer, so all of our local references will be off that fixed, for this execution of this function, base pointer. And our stack pointer could change depending on what happens. But this proceeds as you would expect. We put 10 into A, we put 64 into B, and we put the crazy value, that was it, 10.45 into EBP minus 4. Then we'll move EBP, which is here 10,000 minus 8, which is hex 64, into EAX. And then we will add that with 10, and then we're done. Cool. Questions here? All right. Cool. We're making good progress. Okay. So we saw in this example that we're clearly storing space in each function frame for the local variables. But the question is, so if you're a function that gets called, how do you know where to go back to? Or why do you need to know that? So what happens when a function is done executing? Does the program terminate? It returns to where it was called from. But as we've seen, CPUs that we talked about are incredibly dumb, right? They just execute instruction, 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 instruction. They actually don't have any concept of function calls or anything like this, right? This is something that we essentially add in memory. And so we need some way to go back to the function that called us. And we need other things too. When you call a function, do you want it to just do something and then return? What do you want back from that function when you call a function? What was that? Return value. Yeah, there may be a return value that you want, right? There may be, and you have to actually pass in parameters to a function. So if I'm a function, how do I know how to grab parameter 1 or A or B or whatever the value is? We need our frame pointer. We also need the return address. So we need to know where to go back to, right? We have local variables and temporary variables. So the idea is the calling convention defines how one function calls another, and specifically who does what in relation to all of these things. So all of these things must be stored on the stack. They need to be stored in memory because the CPU has no idea about any of this stuff. So we need some kind of calling convention. It's super annoying because this varies based on processor, operating system, compiler, or even type of call. So for instance, as we saw with syscalls, when you're making a syscall into the kernel, into the kernel, you call int 80 and you put the syscall you want in EAX, and then the other values in EBX, ECX, I think maybe EDX, I actually don't know, I have to look that up. But you put the parameters you want to pass into registers. However, the normal calling convention for calling functions in Linux does not use registers, it uses the stack. But this changes now on a 64-bit operating system, which has a different system call entirely. So you just have to look this stuff up. This isn't something you just magically are born knowing. You have to like study these things and think about it, and you look at enough code, and it kind of becomes second nature. So the idea is the caller first pushes the arguments onto the stack in order from right to left. So if you think about it, the rightmost argument will be here, and then the second one will be underneath that, and then underneath that one, 4, 5, however many arguments there are, right? Because the stack is growing down. Then the caller, as a byproduct of the call instruction, will push the address of the instruction after the call. So this is super important because this answers the question, where do we start executing after this function call? The callee, the function that gets called, it's their responsibility to save the previous frame pointer, if they're going to use it, to create space on the stack and ensure that the stack is consistent. And finally, which actually is surprising because you pass arguments onto the stack. You pass arguments to a function by putting them on the stack, but you actually put the return value in the EAX register. So, I don't know, just stuff, like, I don't know, you have to, there's all kinds of architecture decisions on who should do what and all this type of stuff, but we won't go into that at all. So let's look at an example. So we'll look at our main again. We'll have a local variable A, we'll set A equal to calling a callee function, 1040, return A. We'll have the callee function with int A and B, return A plus B plus 1. So when we compile this, and we'll run object dump on it to look at the assembly, we can look and we'll see push EBP, move the base pointer to the stack pointer. No, stack pointer to the base pointer, sorry. Move the stack pointer into the base pointer, subtract 18 hex from the stack pointer, move ESP plus, move 28 onto ESP plus 4. You know what, we'll just look at this and then, rather than me just keep talking about it. Okay. Right, so the first thing, so important parts when you're looking at assembly code. So almost every function will have an incredibly similar prologue here, which essentially first, because main is a function like any other, right? It has to return. Somebody actually calls main and sets the exit status of your process to whatever you returned from main, and that's how your process's exit status gets set. And so main itself has to follow the calling convention. Main itself has to first store the previous caller's base pointer. So this is push EBP, which is move the stack pointer down, push the base pointer there. Then move the current stack pointer to the base pointer. So basically setting up wherever you are on the stack right now, this is now your base pointer for main. And then you create space on the stack for you. So you move the stack pointer down by 18 hex. And then we have a function at the end, which is called the epilogue, which essentially redo everything that the prologue did and gets us back. But we'll go through there in a second. The other function pushes EBP. So again, right, this is what you have to do every single time. Push EBP, move the stack pointer to the base pointer, then move EBP plus C into EAX, move EBP plus 8 into EDX, basically add EDX plus EAX, move it into EAX, add 1, pop EBP, and return. So again, a prologue and an epilogue. So why is this using EBP plus 8 and this is using EBP minus 4?
The different.
Yeah.
The base pointer is pointing basically
So what would you say that EVP plus 8 is in Kali? One of the arguments of the function, right? Exactly, because the base pointer, as we'll see, the base pointer will point into the function frame, and above that base pointer, right, positive increments up the stack will be the arguments that the caller passed in, whereas negative offsets from there will be local variables local to that function. So this EVP minus 4 is this local A value, and this, I don't know which order this is, it actually doesn't matter, but 8 and C are either A or B. Cool. So we can look through this to see what happens. We can see that actually if we do object dump, we'll see that these bytes get compiled, and we saw that the ELF header will specify that these instructions must be in the program at these fixed locations. You can check this out. I don't remember what version I did this in, so if you do this on your own, you will get completely different numbers, just FYI. And also, depending on your GCC version, you'll get different output as well. Cool. Okay, so we have our handy stack, we have our registers, we are ready to virtually go. So, let's say our stack first starts at FD2D4, so that will be the current stack pointer. Main is called. And we know we're at this instruction because the instruction pointer will have the address of that instruction. Then when that instruction executes, let's say the base pointer is something, whatever, doesn't matter. We push EVP onto the stack, we move the current stack pointer to the base pointer, thus setting up here in our base pointer our local main base pointer. We subtract 18 from the stack pointer, so now all of this is the main function. We then move 28 into ESP plus 4, so that's stack pointer plus 4, which is up here. We move 10 into where the current stack pointer is, and then now we're going to call the function. So what have we done to the stack right before this call?
Wrote the values that were passing into the function, call E.
Right, so exactly, so which one's which?
It reads from right to left, so would...
It pushes it on from right to left. So which one's which?
So the OX28 should be the leftmost, the first parameter that gets taken in by the function call, but I don't know.
No, close. Other way around. So it pushes on it from right to left. So the rightmost argument was int b, right? And so int b is pushed first, which means it will be the topmost of these arguments. And then the argument after that, the leftmost argument, which is a, which was is a and it's hex a, thanks, is pushed onto the stack. Oh, I should have done this so this was b, but we'll push that onto the stack, so we have hex a here. So now when the callee function executes, it knows how to fetch both of these values, and it knows that the first argument will be this one, and the second argument will be 4 above that. But we need to leave a breadcrumb. We need to know, we just can't start executing from 804, 8394, because where do we want to go back to? After callee executes, where do we want to go back?
To where callee was called from in main.
Yeah, where specifically?
Hex 80483BF.
Yes, hex 80483BF. That's the instruction we want to execute after callee is executed. But how does callee know to go back there? Right? There's no magic here, right? We can't just magically try to signal where we want it to go. And so this is why the call instruction here is different from let's say a jump instruction. So you could have a jump to a location. But here we want to call this function. So basically it does two things. It sets the instruction pointer to whatever this value is, and it pushes onto the stack what we call the saved instruction pointer, or the next instruction that we want to execute after callee is done executing. So that's where this 80483BF came in, because this is where we want to go, right? This is our way to tell the function that we're calling, hey, this is where we want you to go back. So you can think of this like a breadcrumb, right? Main is like leaving a little breadcrumb so that way the program knows how to go backwards. And so callee's gonna do its thing. It's gonna push EBP, it's gonna move stack pointer to base pointer to set up its own stack pointer. So we can see from its current base pointer here of FD2B0, so we can see where that currently is the saved base pointer of the previous function frame, and above that is the saved instruction pointer of the person above who called it, and then finally the arguments from left to right, because now we're going up the stack, right? So this is A and then this is B. And so this is how it knows, okay, here's main, here's callee, and so it knows, great, move EBP plus C, so C should be 28 here, so it should be 28 to EAX. 8 will move A into EAX, add them together, add 1, pop EBP, so now we're actually returning from this function. So we're going to set the base pointer back to whoever called us, and now is the most critical part when it comes to security here. Is that now, because remember, again, callee, does callee know that it has to go back and start executing at 80483BF?
No.
No. What does it know that it has to do next?
Go to whatever's in that address.
Wherever the stack pointer, whatever value is currently at the stack pointer, that's where we want to go execute next. Right? Because callee doesn't know. This is the whole point, right? Your functions aren't designed to be called from only one location, so it's just hard-coded to go back, right? Functions designed so that it can be called by anywhere in your program. So the idea is the return instruction literally just, you can think of it as a pop EIP. So take whatever value is currently on the stack, put it in the instruction pointer, and just start executing from there. So that will then move the instruction pointer here, and we'll do the same thing. We will move that into EAX, do that. We'll do a leave, which is the opposite of these two steps, which I'm not going to go into too much. And then somebody called main. So what's the value that's right above, right at FD2D4? Do we know what it is? Like the hex value that's there? No. Do we know roughly what it should be? Is it just random bytes? Yeah.
Probably going to be, it's going to be the same instruction pointer for the function that calls main.
Exactly. And that's what we'll go execute, right? Main's job is done. It doesn't care who called it. It just knows, okay, when I call this return, I'll just go execute from whoever called me. Great. So now what happens when we overflow a pre-allocated buffer? So we've given ourselves a character buffer of 100 characters or something on the stack, and we overwrite it with whatever, 200 characters or something. So normally it's going to cause a segmentation fault, which was maybe the bane of your existence for the first couple times you did C and C++. And maybe it still is, hopefully not, but it definitely still happens, so don't feel bad. So we already know, okay, if we can give input to a program to cause it to just crash, that's an availability attack, right? Which is good, that's something we want to find and prevent. But we can actually specially craft this in order to jump wherever we want in the program. And the idea is that whatever we execute is executing with the privileges of that program. So if it's a setuid root program, then if we can trick it to somehow execute code of our choosing, that code will have permissions as root, not as us. All right, cool. So now we need to look at this. So basically the saved base pointer, so the previous function frame's base pointer and the saved instruction pointer are stored on the stack. And we can control them. So I think about this like, I think I've done this before, but how many people have heard the story of Hansel and Gretel? Yeah, I didn't think we were talking about fairy tales, did you? read up on fairy tales or something. Anyways, the idea is you have this, I don't know, brother, sister, doesn't really matter. These kids who go to the forest, it's a dark forest, and they're scared. So they want to be able to find their way home, so they very smartly take a piece of bread, like a loaf of bread, and as they're walking every feet or so, they leave a piece of bread on the ground, right? Which is great, because they can go out, do whatever they want, and then to get home, they just follow the bread trail home, right? What's the problem with that plan? It's no problem, it works out fine for them in the end.
Somebody's gonna get the breadcrumbs.
What was that?
Somebody else is gonna get the breadcrumbs.
Yeah, well, what happens if either a person or even just birds come and eat that bread, right? Now, you get to a point and you're stuck and you're trying to follow the reverse trail home, and you get to a point and you're stuck and you don't know where to go, and now you're lost in the woods. Or if either a malicious person or a very smart bird is able to rearrange those breadcrumbs, maybe take their own loaf of bread and make reverse breadcrumbs like right back into your oven or something so you can cook and eat these children, which is essentially what the story's about. I'm trying to entice you, not tell you everything, so you can go read it on your own. And that's exactly what we're gonna do here. Cool, okay, so we're gonna have a function myCopy that copies its argument onto a 4-byte character buffer. We will have, I did this a long time ago, sorry. No, we're gonna update it. So we're gonna pass in myCopy in this string into myCopy. It's gonna copy it onto a 4-byte buffer on the stack, and we just wanna see what happens. So looking at the assembly, we have so we can see here we have our epilogue, then we're moving this value, which is presumably the location of memory of this character pointer. So this is gonna be the bytes at this memory location will be the bytes ASU space CSE. We'll call that function. We will then call printf, and then we will put 0 in EAX, which is gonna be return 0. Whereas myCopy will do its thing. And the important thing to do is look at how this actually works. So we have similar situation. So we now have our instruction pointer here. We're going to do the prologue. We're going to save the base pointer. We're going to set up our base pointer for our currently executing function frame. We're going to create space on the stack for our local variables. We're going to move 804, 8504 into ESP. Then we're going to call myCopy. Right? So why did this value get here on the stack? 804, 8423.
It's the return instruction pointer.
Yes, it is the saved instruction pointer, which if we look, it should be 804, 8423, so it should be this instruction. Because main wants this instruction to execute next, right? So myCopy starts executing, it goes great, doing my copy, doing my thing, I need more room for a stack because running stacks are hard. And then I get here, I finally call string copy, and so we can see here. So I put 804, 8504, so this is the pointer, the memory address of the string, that long string we passed in. What's this FD2AC value? Yeah.
Where you wanted to return after call string copy?
Nope. We didn't actually call string copy yet.
Oh.
Yeah, that will be next. Push the string copy on there. But we're not going to show that. It's too many levels.
It's EAX, right? It's looking, which is the argument that string copy is going to return, or it's the.
So we're right about to call string copy. We haven't actually called it yet. So before we call the function, what do we need to do?
The address of the buffer we want to copy the string to?
Yeah, we need the source and the destination buffer. So if we looked at string copy, we'd see that the rightmost is the source, and the other one is the destination, so FD2AC. So FD2AC is here. So this is our character buffer that we allocated on the stack way back. string copy, does string copy know that our buffer is only size 4? What does string copy do?
Puts bytes and buffers,
Puts bytes and buffers until when? How many bytes?
so there's no more bytes to put.
Not quite, close. How does it know that there's not any more bytes to put?
There's an alternative.
Null, yes. So basically, string copy, you could write this. It's very simple. You just literally dereference the destination, copy it into source, or you dereference the destination, check if it's null, you return. Otherwise, copy it into the source, increment both pointers so you're pointing to the next byte, and you just keep doing that over and over and over again. Right, so it's not bounded by the size of the buffer, right, the destination buffer. It's bounded by the size of the input. So when string copy returns, what happens? So we know at 0804, 8504 are these bytes, followed by a null byte. And so what's going to happen? Well, just like we said, string copy is incredibly dumb. It's going to copy ASU space here, and then CSE, and you can actually see, you know, these are the actual hex representation of that there. And is it going to stop because it says, oh, this was only 4 bytes long? No, it doesn't know. It's just copying memory, right? These things are, there's no internal concept to a C string of the length or of the size of the buffer. I guess there is with the length. The length is up to a null byte. So it's just going to keep copying, right? And so it got rid of the arguments, and just like our story, the saved base pointer and the saved instruction pointer, right? So just like our example of birds coming and blowing away bread. Losing my metaphors here. Right. We've completely overwritten the saved instruction pointer and the saved base pointer, and actually we're just going to keep overwriting things. And then string copy returns, and it's fine because so string copy knows where to return to because we didn't put it, but the instruction pointer will be here. So my copy's instruction pointer of 804, 840C will be stored here, so that gets returned to correctly. Everything actually goes just fine. We execute these next instructions just fine. We do a leave, which actually takes the fall and puts it into the EBP, which now makes our base pointer point wherever. And then we get to a return where the program will start trying to execute at 3130, 3220. So what happens then? What does that mean? Crashes, segmentation fault. It's going to try to access some memory that's not allocated to the program. In our analogy, our program is now lost in the woods and doesn't know where to go, so it just blows up. And you can actually do this if you run this example. If you run it, you get a segmentation fault. If you run it in GDB and debug it, you will see that it actually has a segmentation fault because it tried to access 3130, 3220, which was the last part of our string. And if we look at all the registers, we'll see that, yep, we changed the base pointer and we changed the instruction pointer. So at this point, we can actually control the instruction pointer and get this program to execute wherever we want. Pretty cool, right? So, functions to keep in mind that are essentially always dangerous. Gets, because you're getting data from the user, and you get data from the user until there's a new line or end of file. So fundamentally, when you're calling this function, you have no idea how big the data could be. So there's no way to properly create a buffer in advance for how large that is. String copy. If the attacker can control the source buffer, they can supply as many characters as they want in order to overflow the destination buffer. sprintf, svprintf, scanf series of functions. Also custom input routines that they're calling even get C, which is getting a character, but if they're essentially implementing one of these things and just adding to a buffer, you can get overwrites there. The question is, so it's very clear we can get it to crash, and that's a good first step, but we want to go further. We want to not just take down the availability of that program, we want to be able to custom control the that program. And so, how do we execute that? So the idea is once we control EIP, it's kind of game over at that point. Once we do that, essentially we can tell the program to go wherever we want. There is an excellent paper which I believe just turned 20, I think. I think so, is that right? Yeah, called Smashing the Stack for Fun and Profit. This was one of the first. It was published in a hacker magazine called Frack. And it's a really good read. I highly recommend looking through it because you can see that even back then, so you think about, we've had this for like 20 plus years, and this is still an incredibly common vulnerability and attack. Okay, so the first, and what I'm going to do here is I'm actually going to take you up to modern day. So your first kind of thought is, well, we want to execute some, so we can control the instruction pointer. We can control where this program goes. So why not just inject onto the stack? So if we went back here, what if we inject onto the stack, instead of injecting ASU, CSE, 340, fall, whatever, what if we injected bytes that actually did what we wanted to do? Let's say it's a root program, it like, I don't know, whatever, gives us a bash shell as root, right? We could inject in here onto the stack assembly instructions, and then just tell the instruction pointer, hey, go to the start of these instructions and start executing them. Which is the first round. So the idea is, this is called shellcode. So shellcode is the name for any kind of code that you're executing that's location independent. Just like we talked about though, the arms race is that the operating system vendors and the defenders said, well great, in order to do this, you need to know exactly where to go with the instruction pointer, to tell the instruction pointer. So for instance here, if let's say the start of this ASU was the start of our shellcode, we would have to make sure we overwrote, I believe it was this one, 3130, 3220, with FD2AC, because that's where we wanted to go execute next. So the idea is, well, what if we completely randomize the location of the stack every execution? That way, you won't actually be able to guess and know where to go. So the bad guy said, okay, great, what I'll do is I will add a bunch of NOPs, like a no-op, which is hex 90, to the start, literally like, you can do 100 megs of no-ops, and then all you have to do is guess your address somewhere within those no-ops, and just like you think of like a slide or a sled, you just start doing nothing until you hit your shellcode and actually do what you want. Which actually on 32-bit architectures is reasonable, and you can even use NOP sleds of like a gigabyte to completely work around the ASLR, so it only takes like 10 guesses to be right, because as we've learned, an attacker only needs to be correct once, right? So then the defender said, okay, that's a good technique. Like the ASLR doesn't really get around that. So what if we, so the main problem is, who wants to execute code on a stack? What's the stack for? Is it for executing code? No, it's for reading and writing data. It's scratch memory, right? Do programs need to execute code on the stack? Maybe. How does, so, probably one of the programs you use most often, a browser, does this all the time. So browsers do what they call just-in-time compile JavaScript code. So actually take JavaScript code, compile it to assembly, and we'll execute it, and that code will either live on the stack or in the heap. And so some programs actually need executable stacks because they want to be able to execute code there. But for most programs, you don't need that. So the idea is, hey, we saw in the ELF that you can, in the ELF file format, you can specify the permissions of all of these memory sections. So just make the stack not executable. Aha. Problem solved, right? Because now you start executing here, and the operating system says error, you're not allowed to execute code in this memory page. So we'll throw an exception, it actually won't work. So, to get around that, but the interesting thing is, but what about all of these instructions? So what do the permissions have to be on, let's say, the memory that's at address 804.84.0E? Do they have to be readable? Yes? No? Maybe? Actually, don't know. Does it have to be? Maybe not, but it usually is. Does it have to be writable? Yes? At this memory address, 804.84.0E, which are the bytes that represent push EBP to the CPU. Yeah, probably it doesn't have to be, it could be, but you know, why? You don't need to change your own code. What about executable? Does it have to be executable? Anybody want to make a stand?
It's an instruction, but it has to be executable, because otherwise it's not going to do anything.
Yeah. The ELF header specifies that app memory address 804.84.0E must be the bytes that correspond to the assembly instruction push EBP. If you want your program to work, that has to be executable. It can't not be executable, right? And are most programs this small? No, they're freaking really big, right? And so the idea is essentially, well, why don't we reuse chunks of the actual code that's executable? And because of the way most programs are compiled, they're compiled where these memory locations, the executable code is at fixed memory locations, and it's not changeable. So that actually led to return-oriented programming. So this is a super interesting concept, and it's actually really awesome. So let's walk through an example. The idea is we're going to use little, what we call gadgets in the code. So something like, I don't know, push something onto the stack and then return, or add one to a variable and then return. And we can basically, you can think of setting up these breadcrumbs in such a way that the existing code does what we want it to do, and essentially we'll call the system call that we want to call. Really great paper. It's called actually doesn't have a great name, but The Geometry of Innocent Flesh on the Bone. And the idea is, in any sufficiently large body of x86 executable code, there will exist sufficiently many useful code sequences that an attacker who controls the stack will be able, by means of the return into libc techniques we introduced, to cause the exploited program to undertake arbitrary computation. So we're not going to talk about return into libc, but basically the idea is you just set up a function frame to call a libc function. I'm going over ROP because this is the more generalized technique here. So how does this work? So the idea is, and so actually what I didn't tell you on that last example, I had to disable, well, did I? No, that's not true. To actually exploit that previous example, I would have had to probably disable some security features like ASLR, this stack randomization, or non-executable stack. So we'll see here an example where we don't need to do that. So the idea is we basically here have a super simple string copy argv1, which is the first argument, onto foo, return 10. So foo is size 50. So we always need to look at the code. So main has push EBP, all this fun stuff, string copy, cool, we'll go through this. So one thing I'm doing is to make this slightly easier is I'm using the dash static flag when I'm compiling this. What does that do? What was that?
Force you to use tag memory.
No. Good guess though. Do you think a executable with, what is this, like 10 lines of assembly code should be 716 kilobytes, almost a meg? No, why is it so big?
Because a little library calls and everything else is loaded.
Yes, because well, specifically because the dash static flag statically links our executable, which means rather than loading up libc and the DLLs, it's not DLLs, but like the SO and the library files that we need at runtime, it actually compiles them all into the executable so everything is there. Which is nice if you're shipping a binary to somebody and you don't know if they have the specific libraries you need installed, but cool. So the idea is we want to find gadgets in the binary that will perform things for us. And we want to essentially encode our shellcode or encode this idea of execve/bin/bash, or bin.sh, because bin.sh is shorter, into the gadgets. So what we need to do, so looking through the system call, when we look at system calls, what we need is we need the hex value B, which is 11, to be in EAX. That tells the operating system we want to call execve. We need the address of /bin/sh into the EBX register. And we need the address of, so this is the argv pointer. So you need a pointer to an array where the first argument is, or the first element of that array is the address of bin.sh. The next thing is null in ECX, and we need null into EDX. Okay, so where do we put bin.sh? Because we need to somehow get that into the program. So we can actually look at this executable. Where am I going? We can actually, we would find it, I don't know why I included this. So surprisingly, bin.sh you can actually find in libc versions. So this compiled version will actually have the string /bin.sh because it's used somewhere in libc. You can find the address of this string in the binary itself, which is super handy. Now we need to be able to write some data. Yeah.
So why are we using EAX, EBX, ECX instead of the stack like we were pushing?
Because we are making a system call into execve. Where are we at?
And that uses a different calling convention?
That uses that uses the system call calling convention, the Linux calling convention. So where was that? Yes. So we need to put the system call, before we call it in 80, we need B to be in EAX, and we need to set these registers up correctly. But we need things, we need to be able to write some data somewhere. Oh, that's right, okay, right, sorry. So, we can actually see, I don't know, that at 08OEA060, so at this memory location will be data we could write to. So we can actually include in our stack the string /bin/sh, as long as we can somehow find a gadget that will write that out to some place in memory. And the place that we can use at a fixed location is going to be this location because we know it's writable. So we can use any memory location that's writable. But we need to find some gadget that will do that. So there's tools that I'll point you to in the end that we could use. So we could find out that actually at location 809A67D, we'll copy whatever's in EAX into the memory location that EDX points to. So this will take whatever's in EAX. So if we can somehow get /bin, that hex value, into the EAX register, we can then force the execution to jump to this gadget, 809A67D, and this little tiny gadget will just copy that to wherever EDX is. So we need to control EAX and EDX. So it's still a lot, but we can get /bin at a fixed memory location, but we need to go gadget hunting some more. So we need some gadget to get data we control into EDX, right? And what do we control in this situation?
Return instruction pointer.
We control the return instruction pointer. What else? What is that return instruction pointer on?
What? Sits on top of the base pointer. Right?
Yes.
But in the function,
What are they both on?
input the buffer.
What memory location are they? What are they? Where's the save instruction pointer live? The stack. On the stack. Yes, we control the stack. We can completely control the stack. We can write more or less whatever we want onto the stack. So what we're looking for is a pop EDX and then return. And it just so happens that at this memory location, there's a pop EDX followed by a return. So this will take, remember, pop will take a value off the stack. This will literally take the value off the stack, put it into the EDX register. So great. So this helps us by now we can put the address of .data onto the stack. And if we looked at this, so basically this is the address 0806E91A. 0806E91A. And if we execute this, we'd see that when we got here, so here's the instruction we're going to start executing as. So what this is going to do is pop EDX. So it's going to take, so let's say this is the first gadget that executes. It's going to take whatever's above that on the stack and put it into the EDX register. Thus, we can completely control the EDX register. And then it's going to return to whatever is above that. Right? So we can actually put the next gadget we want to execute the instruction pointer, the pointer to that instruction on the stack. And so essentially we're creating this stack of all these little tiny instructions of take this value, put it in this register, copy this value over here to get us to do what we want to do. So, so using this, but we still need to get our data into EAX. And it turns out there's a pop EAX return at this memory location. There's a pop EBX return at this memory location. The crazy thing to think about is, remember, x86 is not a fixed length architecture. So even if you have a really long, that does not necessarily mean that these instructions actually exist in the code itself. It just means that there could be a 5-byte instruction, and this pop EDP return is only 2 bytes. So as long as those 2 bytes that you need occur anywhere in executable code, you can jump to the first byte, and we'll start executing. We can find all of them, pop EAX, pop EBX, pop ECX. We need some way to clear EAX, and a really great way to clear a register to 0 is to XOR it with itself, which happens to be at this memory location. But we need, what do we need to be inside EAX? Not just 0. $11. I don't know what fingers work. We need 11. We need hex B. So we can find an add 10 to 11 to EAX, but that's highly unlikely to happen. Instead, if we find an increment, we can just call this 10 times on our stack, or 11 times. And we need an int 80. So this is actually all we need in order to build a ROP, what they call a ROP chain. So you're going to get a chain of these little gadgets to completely take over this code. So we actually want a Python script to do this because doing this by hand is super annoying. So we can use this pack. So the pack will make sure that the endianness is taken care of. So the first thing we're going to do, this is pop EDX return. So this is the address of data. So this is where we want this to go. So this is going to copy. So this gadget is going to copy whatever's after it into EDX. Then the next gadget that executes, this return is going to execute this next gadget, which is going to take whatever's after it onto EAX, which is /bin. Then we need to call our move instruction to have copy /bin into EDX. We then copy //sh. This is a little trick that I didn't get into. Usually you want /sh0, but oftentimes you want to avoid null bytes. So you can use //sh, which is exactly the same. So we can copy that, add to data +4. So we're going to do our same thing again with //sh. We're going to zero out the thing after it because remember we need, and so we could do that, XOR it, move that there. Now we actually have a null terminated string /bin/sh at this fixed memory location. But now we need to build our array, so we need to build our array, and I'm just going to kind of go through this, you can step through this. We need to, so now this is building up the argv pointer, which is a pointer to pointers, so this is a pointer to an array of pointers. And now we'll finally have, we'll be able to call execve with the address of data with the string bin.sh, the address of .data +12, which will be our array, and we know it at data +8 is a null byte. So this will be, so we need to first get the address of data into EBX. We then get the address of data +12 into ECX. Third argument, EAX, we're going to zero it out again, increment it 11 times, like I said, and then finally call int 80, which will trigger the execution of our code. And so what we can do, we can set a breakpoint at this location. We can run this program with this as input, and we can see right before it returns what's going to happen. So we can see the stack, right, is essentially all of these little gadgets, and so it's going to essentially go through every single gadget doing exactly what we said, putting tiny bits, so you can see like the instruction pointer, so these are not in contiguous memory locations, right? I'm just doing this for show here. You can see this is at 806, this is at 80B, 809, 805, right? But the stack has pointers to all these little gadgets that are executing. And it's just going and doing whatever it's supposed to do. It's executing executable code. It's using fixed memory locations. We can see that at that memory location is the string /bin//sh. We can continue, and we'll see that it's actually executing a new program, which means we successfully exploited this buffer overflow. And it's a fully address space layout randomization proof ROP payload, because no matter what the stack is, we actually don't care because we're only using fixed locations. So you should not have to write this by yourself. I wanted to show this to you. There are tools called ROP-Gadget and ROPR, which basically you point them to a binary. They will try to find as many gadgets as they can, and if possible, actually automatically generate a ROP chain to get a /bin/sh. So it's really cool. Yeah, I actually use those a lot. Cool. Yeah.
Kind of jump past it, but arc injection. So if they've disabled stacked execution, but there are, let's say, a call to the function system in the short snippet of code, without an executable stack, you can still modify the parameters going into that call to the system function to take control of the execution flow that way.
If you know where the system call is actually located, which it depends. Sometimes you can know, sometimes you can't. And oftentimes what you'll actually need in the real world is multiple exploits and vulnerabilities together. So you may need one vulnerability that leaks data and leaks a pointer, so that tells you where the location of everything is, and then you can break that by kind of jumping to where that location is. So yeah, I need to focus on one thing, I think, and ROP is definitely, like, this is the most real world type thing that you can do and get to, so this is why I wanted to talk about this here. Because it bypasses almost all of the current, and there's all kinds of variations, so to go briefly. Research in this is to automate all of these, so we have a new professor in the department who you may not know yet because he just started, Jan Shoshishtashvili. He led the DARPA Cyber Grand Challenge team at UC Santa Barbara, where they got 3rd place and won, I think, a total of $1.5 million by creating an automated hacking system, which basically, so these were completely autonomous systems. There was 10 teams. They each had access to a number of binaries, and their system had to find, identify vulnerabilities in those binaries, automatically synthesize exploits that would work against the other teams, and also inject patches into their binaries to properly patch the binaries. And then you would get, if you chose to patch, you would get everyone else's patches, so you could actually try to find maybe vulnerabilities that were still left over from their patches. So super interesting process. How to exploit these automatically, how to create better defensive techniques, how to combat the problem of multiple vulnerabilities and information disclosure, all this kind of stuff. So it's a super awesome research area.